This meeting is now being recorded.
Today we have Rob Goldston from Princeton, who's going to be talking about verification at large gas centrifuge enrichment plants, which is a particularly interesting topic given concerns both about Iran and North Korea these days in the news. So, Rob, please.
Okay, I'm going to talk about some work I've done with Mark Walker and some association with Alex Glaser here at Princeton about Breakout, which is something we heard about in the Iran deal, but this is more general, and timely verification at large-scale gas centrifuge enrichment plants. They've gotten a lot larger than they used to be, and so this has become a more interesting and difficult topic to get timely verification. So I'll start with some basics, both of what the IAEA does in this business and also about how centrifuges work. This will have essentially all the algebra in the whole talk, so if you make it through the first couple of slides, you're in good shape. So, in terms of the IAEA, when they do safeguards agreements, the fundamental idea is to get timely detection of the diversion of what are called significant quantities of nuclear material, and then deterrence of such diversion by the risk of early detection. And so in this context, we'll talk about SQs, a significant quantity, which is 25 kilograms of uranium-235 contained in uranium that's enriched to over 20% in U-235. The question of what is timely or not is a subtle one, and we'll get into it. So the next thing to talk about is another subtle thing, which is gas centrifuges. And so again, this is one of the more complicated slides, but since we'll be talking about tens or hundreds of thousands of gas centrifuges, it's worthwhile getting an idea of how they work. And besides, David told me if my basic hypothesis is baloney, if I've actually taught people something, that's useful. So here's the teaching people something part, those who aren't experts in this area already. So if you rotate a cylinder with gas in it extremely quickly, very fast, the heavier, in this case, uranium hexafluoride, which is the gas used for enrichment studies, very convenient that fluorine, for example, is mononuclidic. So any change in mass has to do with the uranium. So anyway, the heavier UF6, the UF6 with 238 in it, uranium-238 in it, builds up on the outside due to its greater centrifugal force per molecule. Now, that greater centrifugal force that pushes the U-238 out a little bit more than the 235, they're both pushed out very hard, but the 238 a little bit harder, that fights against diffusion, which tries to equalize the mixture by flow of each species down its own gradient, trying to make it flat. But each one, its diffusion fights with its centrifugal force. So you get a little little more U-238 on the outside. But the key trick is not to just settle for that. So what you do, and this is a for example, because there's different ways to do this, but you want to set up a counter-circulating flow. So you heat, for example, the inside bottom gently. You're not pushing this too hard. And you can see in the diagram that the flow on the inside, it's a little hard to see, but the flow on the inside is going upwards because of the heating in the core on the bottom. But then you cool it on the outside so it falls back down again. And this sets up a slow up-down counter-circulating flow, much, much slower than the rotation. Now, what goes on during this is there's this inner column going upwards, and it's losing its U-238 to the outside on average, and the outer column that's falling down, or the outer cylinder, if you like, that's falling down, is losing its U-235 to the inside. So there's this up and down motion and this cross motion. And as you go towards the top or the bottom of the centrifuge, you're still doing centrifugal separation. The 238 is being pushed out harder than the 235, but it's working on already separated material because it's already happened on the way up. And so you get a multiplying effect. You get way more separation. You get much larger top-bottom isotopic mix difference than you would get from the simple steady-state in-out equilibrium. So the trick then is you need this very, very tall cylinder. You fill it in the middle, and you scoop the uranium hexafluoride gas out at the top and bottom. the picture, you can see the input and the output come from the top because you've got a coaxial cylinder in the middle there. It's confusing or difficult to have it come out both sides. So this thing spins very, very fast and is subject to instabilities. Early ones would start crashing and knock down their neighbors. This is a pretty difficult problem, but it's been largely mastered. And that's the sort of fundamental ideas. But now, if you want to get something done that's meaningful on the scale of what you need for a nuclear power plant, or for that matter, for a nuclear weapon, you need to put a bunch of these centrifuges together into what's called a cascade. And the picture on the right is a cascade, and each of the little rectangles in there of different colors indicating enrichment, are centrifuges. So the basic idea is we're going to put these centrifuges together and we're going to gang their work together. So what is the work? So fundamentally, centrifuges work on this parameter R that's here, which is the ratio of, you can choose it either way, but we just choose it as the ratio of uranium-235 density to uranium-238 density. So that's this parameter R ratio. And then we can define the gain of a centrifuge. And the word gain is used 6 different ways in the literature. So here's the simplest way to think about it. The gain of most centrifuges is symmetric in the following sense, that the ratio of the product to the feed, the ratio of the ratios of R product to R feed is this number alpha. And then that's the same as the ratio of the feed to the tail. So the feed is more enriched than the tails, and the product is more enriched than the feed by the same ratio. And that ratio is typically not a big number compared to unity. That's why you need lots of these. So we conventionally call this 1 plus epsilon. And epsilon is kind of the thing you're doing that's better than just doing nothing, right? Because if alpha is 1, you're not doing anything. Now, in each centrifuge, you obviously have to have the flow of U-235 in and the flow of U-235 out, and the flow of U-238 in and the flow of U-238 out to balance. And with the assumption of the alpha that I've shown there, and now the assumption, or just the definition, that the product flow over the cut, which is the product flow, whoops, this is wrong. It's the product flow over the feed flow. I should change that. So it's the fraction of the feed that goes into the product. That's got to be this theta, and I've done it for the symmetrical case, where you have the same gain going up as, so to speak, from the tails to the feed. And this just follows from the math, and it's the product flow divided by the feed flow. So now what you're going to do is connect all of these centrifuges in a series parallel form, like you see on the right, to form what's called an ideal cascade. And what that means is that the product from any one stage feeds the feed of the next stage, and it's going to be alpha times more R going upwards, and the tails of a given stage feed also into the feed of the stage before, and that's alpha less enriched, so that all works out fine. But we're now never mixing anything. We're never mixing anything with different R's in it. And so you can think from a thermodynamic point of view, we're not wasting work. And that's what a symmetric cascade is. And if you have that, then the work that it does, and the definition of the work is down below, 1/2 the feed rate times this epsilon squared, summed over all the centrifuges, it just all adds up, and that's the separative work unit capacity of your system. There's a more conventional definition that is completely equivalent that says that there's a value quantity, this term with the MP on it, which is the value of the product, and then the next term is the value of the tails, and you subtract off from that the value of the feed, which was what you started with, and that's telling you the work that had to be done to create that product and that tails from that feed. And that turns out to be this sum over the centrifuges of their capability. So that's the basic idea with some of the little more bells and whistles than sometimes people see about how centrifuges and cascades work. So now we're interested in cheating, or we're interested in seeing how someone might cheat. So what are scenarios for rapidly producing highly enriched uranium from systems like this? So we're going to start with a reference large-scale gas centrifuge enrichment plant. So this is a big baby. This is one that can do 30 reactors. It produces about enough separative work units per year that it can provide, round numbers, 20 tons per reactor per year of enriched product for 30 reactors, 20 tons of uranium. So we have, looking at this column, we have one GCEP, one gas centrifuge enrichment plant, which does 4,000 ton SWUs. So before I was talking about kilogram SWUs, so this is obviously 1,000 times bigger. So it's like 4 million kilogram SWUs. The number, they tend to break these things into units. And so one, and there might be in this one that was defined by Smith, Lebrun, and Labella in the Journal of Nuclear Materials Management. These are serious players. Lebrun, for example, does enrichment, planning for safeguards for the IAEA. So these guys laid out this sort of reference large-scale GCEP. So it's got 8 units, and we're going to mostly focus on a unit at a time because it's really hard to connect between units. And then each unit might have 10 cascades in it, and each cascade might be good for 50 ton SWUs per year. So again, 50,000, if you like, kilogram SWUs per year. And just for specifics so that we could do calculations, we've made a reasonable assumption, I think, of 1,000 centrifuges per cascade. So remember, there's 10 cascades per unit and 1,000 centrifuges per cascade. So I guess that's 10,000 centrifuges per unit. And each centrifuge does 50 kilogram SWUs per year. That's pretty juicy. It's not as powerful as the most powerful ones that are around. For example, the Iranian one that they're currently running is about 1 kilogram SWU per year. They're working on ones that could be 10 or more. For definiteness, we're taking 11 enriching stages. Remember that shape had centrifuges going upwards and downwards. Upwards gets you towards the product. We call them enriching stages. Stripping stages are towards the bottom. I warn you that in the literature, people use stripping for the top. It's pretty confusing sometimes. But anyway, 11 going up, 4 going down, and we're going to assume the maximum enrichment, which is pretty much what people want for at the most for reactors these days, is 5%. So that's what one of these units looks like, that next picture. It is a big hall, and it has a lot of centrifuges in it. Some things to look at here that we're going to talk about later are you can see that above each bank of centrifuges going from left to right, there are 3 lines that are shared between, it might be 4 centrifuges across here, I think, and then quite a number of centrifuges from one end to the other. So this is probably one stage of a cascade. It is got product, feed, and tails, and you can see they jump to a different location for the next one, just like we were talking about how the product goes up and the tails goes down. Worth noting is that they're very thin little wires, or really tubes, that carry the product and the feed and the tails to these what are called cascade headers. So we're going to talk about them a little bit in the future. And another thing to notice is that the cascade headers ultimately end up over here on the right. They go into a room that goes parallel to this on the right-hand side. So that gives you the little more big picture. A lot of centrifuges going extremely fast in this room. Mark Walker and I got a chance to visit one of these places. It's pretty astounding. So let's take that picture that we've seen and turn it into more specifics. And there's sort of three areas that are connected. We just looked at the Cascade Hall, and that's this, I've got a little diagram of Cascades kind of here, and there's 10 Cascades, remember, in this unit. And they feed into headers. They feed into unit headers. They have their own headers, which are the vertical lines in effect here. And they feed into headers that go with the whole unit. So this is, for example, the green one here is the feed going into all of them. It's a header for the whole unit. It feeds every one of these. And then there's product coming out, which is the red line coming up out of all of these. And there is also tails coming out. Now, there's more tails than product because, let's say, how to say this, you're trying to concentrate the uranium a great deal, and so you don't have very much U-238 coming out with your product at 5% enrichment. And then up here at the top is the feed and withdrawal station. So here on the left, the green ones, you have these chambers, and you got a picture of one a little later, that we heat up, or that they heat up, and uranium hexafluoride sublimes out of there, and you pump it along into the system. So that, for example, feeds along the green line down into this header connection area, we're calling it. And in this header connection area, that feed goes into each of the centrifuges, the cascades. And tails, by the same token, come out into this set of feed and withdrawal stations, and product comes out. We've got three areas: the Cascade Hall with its headers that you saw the picture of, this header connection area where all the unit headers are. The things that leave the Cascade Hall go to these unit headers that do the whole unit, and then those unit headers head out, so to speak, and are connected up to the feed and withdrawal stations. So that's the sort of wiring diagram or plumbing diagram of how these things work. And, of course, if you're going to cheat, you're going to have to do something with this plumbing. So now then we want to cheat, or somebody wants to cheat. And what they need to do is enrich uranium not up to, say, 4.2%, which is kind of typical. Somewhere between 3 and 5% is typical. But they want to enrich it up to 91%. And they're going to do it in stages, in steps. You'd have to really replumb the whole thing to turn it into one cascade that would go the whole way. But you may remember, if you're reasonable, you probably don't remember it, that the cut, the fraction of the product divided by the feed to each cascade, that cut that you're supposed to do to make this all work, to make it be that top-bottom symmetric, that cut depends on the enrichment level, depends on R. R was in the equation for the cut. So if you are running at low enrichments, from 0.7% to 4.2%, you get a cut that is relatively low going upwards. And so from stage to stage, it gets smaller and smaller because you're like putting less up there, right? And so you get this characteristic shape of what a cascade looks like that I showed you a few diagrams back. But interestingly, if you're going to much higher enrichment, above 50%, first of all, the curvature reverses. Instead of being a concave shape to the top, it becomes a convex shape to the top, and similarly it reverses on the other side. And it's really different. It has a much higher ratio of centrifuges. This is, some numbers of dozens of centrifuges. Many more centrifuges up at the high end than the low enrichment. So there's discussion in the open literature about maybe just replumb the cascades, move around the centrifuges so you can make this shape out of that shape and run different pipes everywhere. That would take a long time. Or another thing you could do is prune the cascades. You could cut back. You can actually take those tubes that I showed you. They're typically aluminum tubes, and you could just crush them with a pair of pliers and take certain of the centrifuges out of service. And you'd have to pay a lot. A lot of these centrifuges are going to be turned off. And the main thing is there'd be thousands of these you had to do that to. And so that would take some time. And, this is Breakout we're talking about. You want to get going quickly. So the other option is just...
Rob, before you go on, I just had a question.
Sure.
To make sure I understand these diagrams.
Yeah.
It's the number of centrifuges on the vertical axis and the stage as you're going to progressively higher enrichment going across the horizontal axis.
Absolutely. Correct.
Is that right? Yeah. Okay. Good.
Probably should have been labeled that way, I realized. When I gave this talk before, I realized that I hadn't labeled it. So anyway, should have been labeled.
Okay. Mm-hmm.
So instead of doing those things, which are most of what's talked about in the open literature, just feed them the wrong uranium. Okay. Take this one on the left, which is what you've got, and instead of feeding it natural uranium, feed this baby 60% enriched uranium, whatever it takes, and just live with it. Now, what's going to happen is that you're going to get an uneven mixing process. You're going to end up mixing together some more enriched stuff with some less enriched stuff. But as it turns out, it looks like it's really worth doing. That this is a smart way to go. It turns out that the gain is asymmetric now and favorably asymmetric. So you've set it up in this funny way, and now I'm going to allow the alpha, which is the gain of the product over the feed, to not be equal to the gain of the feed over the tails. It wasn't sort of fundamentally required. That was what was done to go with a symmetric cascade. And if you allow this intellectually as a possibility, then you can again write down conservation of isotope masses, conserve the U-238, conserve the U-235, and just do some arithmetic. And now you get the theta that would be appropriate if you had this asymmetric cascade centrifuge. You got a centrifuge that's asymmetric. I want no mixing. This is what theta should be. But from the whole story I told you about how these centrifuges work, if I suck out too little at the top or too much at the bottom, I'm not going to change things much because the stuff circulates around and around and around and is just slowly peeled off. So the ratio of the bottom to the top is kind of built into the system. So alpha times beta, which is the ratio of the product to the tails, that's going to be a constant. So now let's consider a case where I've got theta that is less than the ideal one. This is the ideal theta for a funny alpha being different than beta. But now I'm running a cascade that's more pinched than it should be. In other words, theta is less than the appropriate symmetric theta, and then this is built into the problem, and then that tells us that beta has to be less than alpha. You can see that because alpha beta is conserved, and alpha is really close to 1, so little changes in alpha aren't going to matter too much. But beta is very close to 1. Remember, beta is this 1 plus epsilon type thing. So this is varying like mad. So if this is low, if alpha asymmetric is low, if theta asymmetric, if the real theta is low and theta asymmetric is what we're going to get, then beta naturally has to be less than alpha. So alpha is bigger than beta because, remember, alpha times beta is conserved. And so what happens is the gain is shifted to the product side. So now I have a system that is actually producing more enrichment and less de-enrichment than a normal cascade would, a normal centrifuge would, and the uranium inside the centrifuge then is more enriched than the uranium in its feed. I'm sucking out just very little from the top, let's say, and more from the bottom than you normally would. Stuff comes in here, and what happens is, since I'm not sucking out so much product, so much good stuff, the thing gets more and more enriched until the centrifuge itself is more enriched than its feed, which is not the normal situation, and that's when you get this asymmetric solution relative to the feed. Relative to the centrifuge, it's the old story, but relative to the feed, it's now more enriched than what it comes out with. So this is a really good deal if you're a bad guy. I have discussed this with my derivative classifier, and it is not classified. Okay, so now I'm the bad guy. So reconnections are minimized, and we're going to look at this and see how a bad guy would do this. So this is the picture you've already seen. This is the feed and withdrawal stations all lined up. This is the header connection area with the unit headers in the second row here, and then this is all of the centrifuges. So what am I going to do if I'm interested in very quickly turning this massive plant into something that makes HEU? So the first thing I do is let me go back here. You can see a little line here that is let's see, I guess this is how the product would go from all 10 of these up into these product withdrawal stations. So I'm going to cut the product line off of the first 9. So that's the next step. Boom. I've cut the product line. Now, before I did this, I dumped all the UF6 out of the system. And what I'm going to do with that product line is I'm going to turn it into the feed line of the 10th cascade. So I've got 9 cascades, each with 1,000 centrifuges, now feeding the 10th cascade. And then, let's see, hold on here. I'm hitting the wrong button. Then what happens is if I stick 5% feed in, 5% enriched feed in, I get 94% enriched product. All I have to do is wheel up the low enriched uranium into the feed and withdrawal stations, into the feed station, and I get to withdraw in the withdrawal station 94% enriched uranium. It's a very, very simple and quick thing to do. Didn't change, for example, the hookup of all the tails from all of these. Essentially moved 2 pipes. And now I've got a system that will make very nicely, very much weapons-grade material. So what have I got? So how much highly enriched uranium above 90% can I get from this reconfigured plant? With steady operation and 2 units reconfigured. So I've got 8 units, remember. I'm going to run 6 standard units. Don't mess with them. They're going to make LEU that I'm going to feed to the reconfigured units. And those tails turn out to be pretty rich, and so I'm going to recycle them through the system. Then I can make 1 significant quantity, which sort of corresponds to a weapon's worth of uranium for a beginner. 1 significant quantity per day for as long as I'm getting natural uranium. So that's, if you waited a month before you went in and inspected this place, this guy would be moving right along. But even worse, suppose you consume stored low enriched uranium. You don't make it as you go, but you've kind of not sent out your LEU for about a month. And you reconfigure every unit this way. 2 pipes in every unit, and now you roll in the LEU, and now you can make 29 SQ, 29 early weapons worth of uranium in a week from, again, 1 month stored LEU and, again, recycling the tails. You could keep going at this rate if more LEU is supplied. So this is not what you would get if you had replumbed everything and made it all into perfectly ideal systems that don't mix and don't waste. This has about half of the ideal rate of production, and it needs whatever that is, 2 2/3 more LEU to do it, but it starts absolutely right away. So that's the thing you're concerned about. So how do you deal with this? The same guys, Smith and Lebrun and LaBelle, proposed 2 real-time unattended monitoring systems. They proposed another one for monthly basis, but let's talk about real-time. So they have load cell monitors. They're going to share these with the operators, and what these do is weigh the mass of the cylinder filled with UF6 that's inside of these feed and withdrawal stations. They're called load cells. And that will tell you the rate at which absolute quantities of material are going away. And in particular, that would show you that the product was coming in rather slowly. It was only coming out of one centrifuge, the one Cascade, instead of 10. So that would be worth something. But they're not really fully independent. You can't, the IAEA likes to have a measurement system. They put a box around the measurement system. Nobody goes inside that damn box. And they detect if somebody goes inside that box. And you can't really do that on a scale that you're sharing with someone else. So that's a concern there. Now, what they have in Iran now, and only in Iran so far, but they'd like to put it more generally, are online enrichment monitors that measure gamma rays from the what's in the pipes. And what they do also is they measure the pressure in the pipes. They have their own little pressure measurement, which they actually share with the operator. But that's intrusive. They had to cut a hole in the pipe to obviously to get the pressure gauge in there. And that's a concern. It might be difficult to do more generally. And you're also worried that the operator could plumb around them. He just makes a little loop around the OLEM and makes that so that it's got whatever it had in it before, but you flow stuff by it somewhere else. So there are concerns about these in Iran. I think it's fine because they go investigate it every day. They can investigate it every day. They do not have enough SWUs to do anything of any significance in a day. So I think it's great, actually, as part of the Joint Comprehensive Plan of Action. But for the longer run, it may not be enough. So what we've been thinking about, what Mark Walker and I have been thinking about, is feed and withdrawal monitors. So this is kind of wild. It turns out that uranium-235 carries along with it about 1% as much uranium-234 through the whole enrichment process, and it makes alphas. And the alphas come out, and what do they find around them? They find some uranium that they don't interact with particularly well, but they find a lot of fluorine. And alphas, when they hit fluorine, in general, alphas when they hit low Z things, can cause a neutron to be emitted. And per ton of uranium-235, this makes 5 million 1 MeV neutrons per second. So that's actually something you can detect. And indeed, if you put a standard portal monitor next to that, like they use in ports for seeing whether somebody's trying to bring a bomb into the country, a portal monitor can detect what's going on inside of this cylinder. It has 8 tons of uranium in it, and remember, there are 5 million per ton of U-235. So we're talking about hundreds of thousands of neutrons coming out per second. And the portal monitor detection efficiency, even 2 meters away, is about 10 to the minus 3. So you can detect whether somebody's putting LEU in here versus natural uranium with 5 sigma confidence in a couple of hours. So you can be pretty confident pretty quickly whether this guy is committing what some people might in general call the cardinal sin of enrichment plants, which is to put something in other than natural uranium. This is really a sin. And now you're in a position, perhaps without God telling you, to yourself know whether the guy is sinning. And these are indeed these feed stations that you're seeing here. Okay. Another thing we'd like to do is measure the flows. And you'd like to do it in multiple places. You'd like a really simple way to measure the flows. In our particular scenario, the feed and withdrawal flows are almost equal. Very little goes into the product. So if you see that, that's a sign of something wrong. And the product is also getting about 10 times less flow than it should, even less than that. And so you'd like to be able to measure the flow rates. It turns out that people do this very, very nicely by putting a hot wire basically into the flow. And when they do that, you measure the power it takes to keep the hot wire at a certain temperature. Now, that won't do for us for a couple of reasons. One is the guy could cheat by changing the temperature of the gas coming in. And the other is the guy really doesn't want you sticking something into the flow of the UF6. UF6 is pretty corrosive. Exactly what's going to happen, who knows, and he's got a huge investment, as you can see from those pictures. So what we did is we looked at the possibility of heating one section of the pipe and cooling another section of the pipe. Turns out that an engineer at the Plasma Physics Laboratory had worked on this kind of idea for flowing water in nuclear power plants, very slowly flowing water in nuclear power plants. So we worked with him, and we did some theoretical calculations using CFX in ANSYS. And you can calculate how much heat, for just a few watts, how much heating you can get. Here's from sort of 5C to 10C heating. And then you put cooling on also, so the guy can't cheat by fiddling with the temperature of the gas. And what you see is that to get to, say, if say you want 7.5C temperature rise, and you have a flow, it's kind of a typical flow of 5 meters per second, then it takes 5 watts of heating and 5 watts of cooling. And it turns out that the heat transfer is, from the basic fluid dynamics, proportional to the density times the velocity to the 0.8 power roughly. And that's telling you that since you know the diameter of the pipe, if you know rho v, you know the absolute flow of mass. So this is incredibly useful for knowing where the flow is going on. Now, you probably would also like to detect if somebody is cheating and reconfiguring things, especially on those areas that we've identified as so sensitive. If there's any kind of a sample port, they have ports that are big, actually. We saw them. They're like 5-inch in diameter ports. And if they have them in the sensitive places where they could do this cheating so easily, you'd like to have some remote indicating seals on those sample ports. You could also, with modern technology, have a camera. This is not the most ideal camera here, but anyway, a camera that would look in areas like that reconnection, the header connection area, or actually even in the centrifuge hall, and see if there was funny things going on, if there was a whole lot of activity going on. And then a totally cool thing is that they now make, for health safety reasons, very sensitive sensors for hydrogen fluoride. And you can have them go all the way down the hall and back again in a mirror. And it's an eye-safe thing, and it detects hydrogen fluoride. And the point is that if you let out a little puff, even a little tiny puff of UF6, it immediately makes a bunch of hydrogen fluoride. I don't have to figure out whether it's too enriched. I don't have to measure anything about uranium, and the HF doesn't carry anything about uranium. But I can know that somebody is doing something. And if they haven't declared they're going to do it, then I know something fishy might be going on. So those are some of the unattended detections. Now this time, these three are reconfiguration detection. So if you're going to select tools out in the real world here for this, you're going to need a graded approach. If somebody has a plant design that's extremely hard to cheat with, or somebody doesn't have much SWU capacity, so it would take them a month to cheat even with our snazzy scheme, then you don't need to have so much in the way of unattended monitoring systems that report in real time. There's a thing the IAEA does called acquisition pathway analysis, and one of the things it can lead to is giving, and that along with inspections, get you to the point where you can perhaps give a country, and many countries have this, a broader conclusion that says that you don't believe that there's undeclared nuclear activities going on, and so they're not ready to take that uranium and very quickly turn it into a weapon. So maybe in those cases you can back off. And if there's an international management system and lots of international engagement, maybe that gives you some confidence also. So you can't go in and say to every operator, I want all this stuff. It's got to be really thought through, and the IAEA has to think it through. They're going to have to negotiate it with the operators. And speaking of which, these things had better not require essentially any maintenance. You think you've got this great thing. It's an unattended monitoring system. Don't need inspectors to go in. Well, if it has a failure rate and the inspectors have to go in and replace it, then it can end up costing more inspector time, not less. It has to have an outrageously low false alarm rate. You cannot have people saying, oh, my God, you're cheating in this enrichment plant, when you're not. That's sort of political suicide. And it's good if it has clear benefits to the operators. they really have a say in this. And so, for example, you could have fewer inspector visits if you really develop confidence in these things. So the next question is, suppose I find out in a couple of hours this guy is cheating. Can the IAEA respond? So talking with lots of people in Vienna, it's clear that you need to be able to do anything, you want multiple measurements. You probably want that Olam, you probably want the flow meter, you want the thing that detects whether there's LEU being fed into this thing, and you got to get multiple anomalies. I really think something funny is going on here. Then you consult with what's called the State System of Accounting and Control, and if you're not satisfied, the IAEA can ask for a limited, can get a limited frequency unannounced access, it's called, with 2 hours notice. And so you could move pretty quickly to take making a confirmation step. Now, this needs, again, an extremely low false alarm rate. You cannot do this by mistake 2 or 3 times. The third time, all the instruments are thrown out of the hall. And the Board of Governors agrees to that. So this is a major issue. But if you do this and the inspectors are denied entry, or they find misuse, then you need to have a political level consultation with the state. That's probably the Director General talking to the Foreign Affairs Minister of the state. And once that's done, you can call a meeting of the Board of Governors, and this was amazing to me in interviewing people, and get that board called within 3 hours' notice. Apparently, all of the Board of Governors live in Vienna, and they understand that this is part of the job. But you sure as heck can't do this unless you have multiple indicators and you've got prior state consultation, so you can say, I've talked to, this state, and here is where we stand, and so I need to inform you at the Board of Governors of what's going on. Once you've informed the Board of Governors, you've informed the whole world. And so that's supposed to be the thing that provides timely detection and therefore deterrence. So, conclusions: a 4,000-ton SWU per annum, 4 million kilogram SWU per annum gas centrifuge enrichment plant can be misused. We didn't try to estimate how long it takes to move those pipes around. I didn't show you, but Mark did some nice calculations of the time dependence of the thing coming up to its new equilibrium, and that's just a few hours, 6 hours, say. So that's not a major piece of this. The piping could take some time, especially if you're doing it over all of these things. You don't want too many people sort of suddenly appearing. But, it might be a day, it might be days, and then it can produce SQs per day, as many as 4 SQs per day in the one scenario. So we think that unattended monitoring systems are critical. The load cell monitors, which are having some difficulty being sort of validated because of this issue of they're sort of shared with the operator, and the Olams, which may be vulnerable because you could pipe around them, they're really valuable and you want to have them. But we think it's probably a wise idea to add feed and withdrawal monitors that can tell if LEU is going in, and in fact LEU is coming out where depleted uranium should be coming out, and then these flow meters. Maybe you want to add some real-time reconfiguration detection. You absolutely need a graded approach. The IAEA does have the tools to respond quickly. They don't have fighter jets, but they do have a means by which the whole world will know rather quickly if you're cheating. And it's just as an afterthought, we should get used to these ideas of unattended monitoring systems. We should make them work, because they'll also be needed to support any kind of a treaty that limits fissile material. Now, if you've already got tons and tons of it, you're not going to make much change in a few hours. But once you get down to low quantities, and you're saying, I've got a ban treaty that everybody's signed on to, you want to know that no cheating is going on, even at low quantities. In this case, we're not supporting just the non-proliferation treaty, but a nuclear weapons ban treaty. Okay, so that's what I've got to contribute, and I'm open for any questions and all questions.
Okay, thank you. If people have questions, I said you can either let me know through the public chat feature or the Q&A feature. I had a couple questions I wanted to start with. One is you've talked about the false alarm rate, and I'm wondering whether you've, to what extent you've been able to get a handle on a couple of the monitors you've been talking about. And I also assume from your discussions with the IAEA, you have some sense of how the IAEA is thinking about some of these proposals you're making. I'd be curious to hear about that.
Let's see. On the false alarm rate, they don't actually hand you the data on that from the existing things. I know that there was a precursor to the online enrichment monitoring system that was having some difficulties. It's a fairly sophisticated piece of nuclear physics that's going on there, and so they had some difficulties. There'd be buildup of material in the pipes, and then that would confuse the monitor because you'd get gammas that came from that. And they've got a new idea for how to deal with that. The pipe naturally changes pressure over time, and then you track the change in the gamma production rate versus the pressure, so you know how much is just still stuck to the walls. So they're making progress on that, but that ran into some difficulties. They have only installed the OLEMs. They did some testing of OLEMs, I think, in existing plants, and then they did install them at Natanz, but it's not one of those things they're putting out in public. Now, as to some of these ideas about feed and withdrawal monitors and flow meters, the IAEA does put out a set of needs to the NNSA, and we're sponsored by the Consortium for Verification Technology in this research, which is through the NNSA. And so we've gotten access to some of this information, and they are very interested in both flow meters that can be fairly accurate and very quick, real time, and also a real-time monitoring of the enrichment level of what's going in. Those are both items that they've identified. So I think those are answers to your questions.
Yeah, and I'm just curious, on an organization like the IAEA, how long does it take for them to move forward with something like this? I mean, is this something that can happen in the next couple of years if they wanted to, or is it a slow process?
They moved the OLEM forward. They knew they thought they might have a need for it, right, if the deal worked, the JCPOA worked, and they moved that forward very quickly. I'd say that was 3 or 4 years. But they've been thinking about it, doing lab stuff, and then they just dragged it out and tested it and beat it to death and put it out there. So that was pretty quick. I've been discussing with the NNSA some ideas we have for I just showed you actually, for the withdrawal monitors and the flow meters, feed and withdrawal monitors and the flow meters. And the first group at the NNSA I talked with said, well, this is actually too simple. This is not a long-term thing. This is a short-term thing. So now we're talking with a part of the NNSA that does short-term things. And they liked their point of view is we fund you year by year, and if by the third year you're not already beginning to test it in real facilities, then we're not so interested. So that's the kind of time scale they're talking about.
Anybody else have a question? I don't see anything coming up.
While
we're waiting, I have one other question, which is this diversion route that you've talked about. Is this something that people haven't really analyzed so much before, or is this something that people have known about and you've been trying to look at how you would detect it?
As far as we understand, this is not something that's in the open literature. But on the other hand, I do have a derivative classifier, and it's not classified. So I think, at least from the point of view of the open literature, it is not something that people have thought about. And I have talked with a bunch of the experts in this area, and they get a little vague about exactly how you would reconfigure these things if you did want to reconfigure them. And so this. It turned out Mark and I sat around and looked at that figure you've seen and went, holy cow, you could just do this. And would that work? And it did.
Yeah, and I'm assuming that if you were a state that had one of these, had invested in one of these big facilities, you would be scratching your head the same way. So
yeah, I don't think this is
right. The fact that it's not in the open literature doesn't mean that you're revealing something here that people haven't thought about, and
the fact that the derivative classifier said this is fine suggests that too.
Yeah.
And it if a graduate student and a fuzzy-headed professor can figure it out in a week, I think a lot of people can figure it out.
Right. Any other questions from anybody in the audience here?
Everybody's stuck.
Well, if not, thank you. It was not only a really interesting conclusion in terms of what you came up with, but I found your discussion of the centrifuge at the beginning quite useful, even though I've seen this stuff before. So thank you for that. And as usual, if people have talks they would like to give or know of somebody who has a talk that would be good for this, please let us know. So thanks again, Rob.
Okay, thank you.